The reason objects and matter in our 3D world tend towards spherical bodies, and why pi appears everywhere, is a property I call dimensional inherency. If we take gravity as an example, apply the Newtonian limit approximation and treat it as a force. In 3D space, gravity acts equally in all directions. To minimize the action, any object formed under gravity in 3 dimensions would inherently produce a sphere, regardless of whether you use rectangular, polar, spherical, or cylindrical coordinates. The minimized action in 3D must always act equally in all directions, producing the perceived, well-known sphere. This is well established and understood, even by the layman. It is precisely what our daily perception of reality correlates to. The interesting question is whether this translates to n dimensions. A further complication, whether the underlying forces actually exhibit themselves in higher dimensions at all. Do they bleed through? And if not, what is the natural, dimensionally inherent minimized shape or geometry in n dimensions? The ultimate economy of space. The sphere is not a geometric accident, nor is it merely one shape among many. It is a structural necessity of the physical universe. This inevitability is rooted first in the isoperimetric principle, which dictates that a sphere maximizes the enclosed volume for any given surface area. When nature seeks the ultimate economy, whether in the formation of a soap bubble or the accretion of a star, it defaults to the sphere. It is the physical manifestation of perfect efficiency, an uncompromising solution to the problem of spatial limitation. Viewed through the framing of least action, the sphere runs deeper still. It is exactly what emerges when physical forces act without a preferred direction. When gravity or surface tension pulls equally from all sides, a perfectly isotropic equilibrium is born. In this context, pi is not a mathematical curiosity, nor an arbitrary sequence of digits that happens to recur. It is a symptom of that symmetry, a structural inevitability that defines how reality balances itself when free from directional bias. Most tellingly, the sphere possesses coordinate independence. Whether we attempt to map reality using rectangular grids, polar angles, or cylindrical projections, the sphere survives the translation. It does not rely on our chosen mathematical frameworks to exist. The sphere is prior to the coordinate system, not a shape produced by our mathematics, but an underlying truth of reality that every mathematical system must eventually reckon with. The upward question. Having established the sphere's necessity in our physical reality, we must ask the upward question. Does this dimensional inherency hold as we scale into n dimensions? Mathematics introduces the n-ball, the solid region of space bounded by the open paren -1 close paren sphere embedded within Rn. Just as the familiar two-sphere encloses a three-dimensional volume, these higher dimensional analogs represent the natural boundary of space in any number of dimensions. The principles that govern our reality scale without friction. The isoperimetric inequality, the rule that a spherical shape maximizes the enclosed volume for any given surface area, generalizes cleanly to higher dimensions. This is not a localized quirk of our three-dimensional universe. It is a fundamental law of space itself, holding regardless of how many orthogonal axes are added to the system. Notably, pi does not disappear in this generalization. It appears in the volume formula of every n-ball, an inescapable signature of rotational symmetry at every dimension. The logic of least action remains unbroken across dimensions. If an isotropic force acts without bias in an n-dimensional space, the resulting shape of minimum action is always the hypersphere. From the lowest dimensions to the highest, whenever a system is stripped of preferred directions and forced to find balance, the sphere emerges as the inescapable geometry of equilibrium. The geometry at least holds. Whether the physics does is a different question entirely. The mechanics of flux. While the geometry of the sphere scales into higher dimensions, the physical forces that might shape it do not. This fracture between pure mathematics and physical reality begins with Gauss's law, which dictates that the total flux of a force field passing through an enclosing surface is strictly proportional to the enclosed source. In our familiar three-dimensional space, that enclosing boundary is a two-sphere. Because the surface area of a two-sphere expands proportionally to r squared, the strength of the force must dilute over that growing area, causing it to fall off as the fraction with numerator 1 and denominator r squared. The inverse square law, therefore, is not an arbitrary physical rule. It is a direct geometric consequence of three-dimensional space. As we scale into n dimensions, this force law is not portable. In an n-dimensional space, the bounding surface is an open paren n-1 close paren minus sphere, and its area scales as r raised to the n-1 power. Consequently, any force radiating outward from a central point must dilute at that same rate, falling off as the fraction with numerator 1 and denominator r raised to the n-1 power. The hypersphere still exists as the shape of minimum action, but the physics dictating how matter interacts within that space changes entirely. The laws of attraction and repulsion are inextricably bound to the dimensions they operate within. This shift in the force law has catastrophic physical consequences. As physicist Paul Ehrenfest demonstrated in 1917, stable closed orbits, the kind required for planetary systems and atomic structures, are exclusively permitted by an inverse square force law. In a four-dimensional universe, where force falls off as the fraction with numerator 1 and denominator r cubed, matter as we know it cannot stably aggregate. Any perturbation would cause orbiting bodies to spiral inward toward destruction or fling outward into the void. The paradox of higher dimensions is this: the hypersphere remains the inherent shape of perfect equilibrium, but the force laws of that dimension make the physical assembly of such a shape entirely unreachable. The boundary of three dimensions. The realization that the inverse square law breaks down in higher dimensions forces a direct question: are the fundamental forces strictly confined to our three spatial dimensions, or do they leak into unseen higher ones? Theoretical frameworks like Kaluza-Klein theory and the ADD model of large extra dimensions propose that forces might bleed into extra dimensions, but only at subcompactification scales. In these models, extra spatial dimensions exist, but are curled and compactified. At distances smaller than the compactification radius, the hard boundaries of our 3D reality soften, allowing forces to propagate into the higher dimensional bulk. This dimensional leakage would alter the behavior of physics at microscopic scales. Below the compactification radius, gravity would no longer adhere to the familiar fraction with numerator 1 and denominator r squared dilution. It would transition to a steeper gradient, falling off as the fraction with numerator 1 and denominator r raised to the 2 plus n power, where n is the number of extra spatial dimensions. If matter were to aggregate at these scales, the altered force law would rewrite the geometry of equilibrium entirely. Responding to an isotropic force in a higher dimensional space, matter would naturally tend toward a higher dimensional hypersphere, reflecting the actual spatial geometry of that regime, not the restricted geometry of our own. This behavior is strictly localized. At macroscopic scales, distances well above the compactification radius, forces can no longer spread into the extra dimensions. Compactification restores standard 3D behavior. We recover the fraction with numerator 1 and denominator r squared force law, and macroscopic matter settles into the familiar, stable sphere. This threshold is not entirely speculative. Precision tests have rigorously searched for short-range deviations from the inverse square law, constraining how large these extra dimensions could be. The sphere we observe in the cosmos may be an emergent illusion, not the fundamental geometry of space, but the macroscopic consequence of dimensions we cannot reach. The geometric anomaly. As we push the mathematical logic of the sphere toward its absolute limits, a counterintuitive phenomenon emerges. If we track the volume of a unit n-ball, an n-dimensional sphere with a radius of exactly 1, we find that its volume does not grow indefinitely alongside its dimensions. Instead, the enclosed volume peaks in the fifth dimension, around n almost equals 5.26, and then begins a relentless collapse. As the number of dimensions approaches infinity, the volume of the unit sphere vanishes entirely, tending towards zero. This forces a radical reconception of high-dimensional space. In familiar low-dimensional geometry, a solid sphere represents fullness, its volume distributed substantially throughout its interior. As dimensions multiply, the geometry migrates outward. In high-dimensional spaces, almost all the volume of the n-ball concentrates infinitesimally close to its surface boundary. The solid sphere undergoes a stark inversion. What begins as a dense, filled volume stretches across orthogonal axes until it becomes a shell of vanishing thickness. Mathematicians call this concentration of measure, not a paradox, but a theorem, and one of the stranger ones. When dimensional inherency is taken to its logical extreme, it produces not infinite fullness, but geometric hollowing. Space, when granted limitless orthogonal freedoms, inherently sheds its interiority. The sphere, nature's ultimate shape of enclosed equilibrium, eventually ceases to enclose much at all. It suggests that in the highest limits of spatial reality, existence is almost entirely a phenomenon of surfaces and boundaries, leaving nothing but emptiness at the core. The solidification of isotropy. The sphere, then, is not merely a shape the universe selected from a catalog of possibilities. It is the physical manifestation of perfect balance. It is what isotropy looks like when it solidifies. Whenever a system is stripped of directional bias, the resulting equilibrium will always adopt this form. Yet, as we have seen, this mathematical truth scales into n-dimensional space while the physical reality does not. The generalization holds for the geometry, but fractures when confronted with the physics of forces and flux. This fracture points to a deeper inquiry. When we look beyond our familiar three dimensions, the mystery is no longer about which geometric shape minimizes action. The mathematics of the hypersphere have already settled that question. The true question is whether the physical forces required to drive that minimization exist in those higher dimensional regimes at all. A hypersphere cannot assemble if the space it occupies destabilizes the forces of attraction required to build it. Ultimately, we are left with a tension between the mathematical ideal and the physical real. The geometry of the sphere is universal, an inescapable truth of equilibrium across any number of dimensions, but the physics that govern matter are stubbornly localized. This asymmetry between unbroken mathematics and fragile physics is not a flaw in the design of reality. It is the very boundary condition of our universe. It is precisely because the force laws do not scale, because stable orbits and the aggregation of matter are uniquely permitted in three dimensions, that we are here to observe the sphere at all.